Good evening. I'm going to talk about thermodynamics of an ideal gas. I will do a monatomic gas and a diatomic gas. The only difference between the two of them is a change in the number of degrees of freedom from 3 to 5. Okay, so I will include the internal energy of a gas. I will keep things dead simple. Maybe the first law of thermodynamics, and depending on time, maybe the next session, specific heats of gases. So, what did we have? So far, we had the 18th century point of view for an ideal gas, and that was this. We always dealt with the quantity, pressure times volume. Now if we look at pressure, pressure is force over area, pascals. Area times dx is volume. So that's like work. A lot of people forget that we should keep that in the back of our minds all the time. And the work is related to what? Let's see. Well, the ideal gas law says it's equal to N R T. That's a constant. Temperature is the only thing that changes depending on how much work you put into this gas. This PV quantity is telling us already that the work here and the temperature are somehow associated. We're going to associate energy and temperature a little bit more closely. Now, I'm not talking about the Joule business where Joule shows that work, mechanical work, and energy are equivalent. That's a separate idea. This is different. This is James Clerk Maxwell. Just after the American Civil War, James Clerk Maxwell came out with kinetic theory of gases. James Clerk Maxwell was born in Edinburgh, and he taught in my old college, King's College London, and he was also the first Cavendish professor, I think the first, well certainly a Cavendish professor at the University of Cambridge. Cavendish, the Cavendish laboratories, that's experimental. The Lucasian professor there at the time, I can't remember, it could have been Stokes, but Lucasian professor would have been Newton, and then nowadays Hawking. Maxwell was Cavendish, or head of the Cavendish laboratory. So, what are we doing? We're looking at kinetic theory due to Maxwell. We look at the internal energy of a gas, some thermodynamical processes, specific heats, and the first law of thermodynamics, which is intermeshed in here all the time. Okay, very good. So we had PV equals nRT equals nKT. And remember that R is the universal gas constant. .31 joules per mole per Kelvin. I'll add another digit in there. If we're dealing with SI units. K is Boltzmann's constant. What is it? K. K has to be joules per Kelvin. All right. So, as well as that, N is the number of moles. T is in Kelvin. We cannot use centigrade unless we deal with the temperature difference. What else? Pressure is in pascals. Pascals are newtons per square meter. And just for the record, 1 atmosphere is just a different unit of pressure, 1.013 by 10 to the power of 5 pascals. Okay? So let's take this to the next level. We'll go to kinetic theory, a very elementary or simplistic point of view. A more sophisticated view on this will look at the Maxwell-Boltzmann distribution of speeds of molecules. But one way or another, kinetic theory says that if we take a system and I'm going to make my system a box of sides L by L by L. It's a cube, so therefore A, the area of a side, is L squared, and V, the volume of the box, is L cubed. Now I'm going to stick a particle in the box. The particle has a momentum of P equals mv. Now, what causes the pressure on the sides of the box? We're going to say that, if you speed up the molecules real fast inside the container, they'll want to get out. They'll create pressure on the walls. The pressure is due to an exchange of momentum between the particles as they collide with the walls and lose their momentum. Now, a particle is going to have mass m. All the particles in the box are going to be the same mass. The velocity of the particles we're going to take out to be an average. I'm going to use the term root mean square just to keep your professors happy. It doesn't matter, it's an average speed. Now what happens when a particle hits the wall of the box? We're just going to look at the side of one side of the box. Now according to Newton's law, the force on the side of the box is given by the change in momentum per second, delta P over delta T. Now a particle comes up with momentum mv. Box stops it. Bang! And there's a change in momentum of mv. But wait a minute, these are going to be elastic collisions. Elastic collisions involve full bouncing. So the molecule bounces back. So the wall gives it two things. It absorbs an mv and gives it another one. The wall accepts twice the momentum, 2mv. So when that molecule, one molecule, hits the wall of the box, there's a change in momentum of 2mv. Now what is pressure? Pressure is force over area. Okay? Now the time between successive collisions is 2L over V because a molecule has to come over and back and again. L and another L. And then bang. 2L over V is the time between collisions. So that the pressure is 2m over 2L over V times 1 over L squared. 2's cancel. Well, L cubed is just the volume. Okay? So now we have the statement. That PV is mv squared for one particle. Or n times mv squared for n particles. Still not quite correct, because this is what we're doing. We're taking all our particles, n particles in the box, 1/3 of them go that way, one-third of them go in and out of the page, and 1/3 of them go up and down the sides of it. 1/3 of all the particles go that way, 1/3 go this way, and 1/3 go that way. 3 degrees of freedom. It was incredible for James Clerk Maxwell to figure that out. He could have got away with not even putting that extra piece of information in there. Now this is true for a monatomic case. What are the monatomic molecules? Helium, neon, argon, krypton, radon, and xenon. The inert gases, none other. Diatomic molecules would be hydrogen, oxygen, nitrogen, and chlorine. That's it, period. So let's move on. Now I'm still recovering from an injury, so I'm moving slowly. Now I've already said that for the one side of the box, we have to divide by 3 to account for 3 degrees of freedom, so I go over here. Now V is root mean square speed. You can go away and look at that. We don't care. For us it's just an average and it's squared anyway, so we're out of trouble. Now let's just divide by 2 and multiply by 2. Okay? mv squared is kinetic energy, and this is an average kinetic energy per molecule. This is the total kinetic energy for all of them. Well, it's N, the total number of molecules, times the average kinetic energy per molecule, U. Now we see something very interesting. Well, it's very clear. T is the only variable here, and the only variable here, these are constants. And U depends only on the temperature, and that is crucial. I skipped a lot of assumptions, by the way. Assumptions of kinetic theory you can find on the web. They would be that the molecules only make elastic collisions with each other and the walls of a container. Momentum is conserved. There are no sticky business between molecules, no strings, no springs, no other interactions, electromagnetic or otherwise. And the volumes of each little molecule is so tiny that it doesn't matter compared to the big picture. Very large number. This n is a huge number of the order of many times Avogadro's number. So, what can I say after this? Oh yes. Very important formula. We put a bracket around it. U is 3 over 2 kT. Actually, that's not quite right. Let me check that on again. N. Okay, there's an N in there. All right. So, NKT. So then, per molecule, EK average is 3 over 2 kT. T is in Kelvin, and K is Boltzmann's constant. Is it joules per mole? Joules per Kelvin. Okay, I'm slowing down a little bit. All right, so far so good. Now that's probably all I need to take it for this particular session. The next session I will deal with what happens, how do we increase the internal energy of a gas. Well, if we change from U to a configuration of U plus delta U, we've increased it a little bit, what goes into the delta U? Answer. We can do mechanical work on it by compressing it. Or we can add heat. This is the mechanical work added to the system, and this is the heat added to the system. And that's a whole nother story. For now, I'm going to stop there. I'm going to formulate the first law of thermodynamics. So to increase the internal energy of a system, and our system could be an ideal gas in a piston cylinder arrangement like we continue to have. It doesn't have to be. But if you want to increase the internal energy of an ideal gas anyway, there are two ways only to do it. You add heat energy. Now heat, of course, is equivalent to mechanical energy by joule. And you can show what the mechanical equivalence is. So really, there's no difference. We're only finding a way to talk to it. And so we can write that when U goes to U plus delta U, what is delta U? Delta U is the increase in mechanical Delta U is the increase in internal energy. It's not a differential yet. So, the increase in internal energy is due to the heat added plus the work done on it. If you compress something, you make it smaller in volume. That'll deal with a sign problem, which we'll deal with it in the next choice. Now, delta U is delta Q plus delta W is the first law. First law of thermodynamics is right here. Now the delta W is negative P delta V, we will deal with in the next situation, but now I'm not sure, I forget what way I formulated this. Let's not put that in just yet. Okay. So for the next class, we'll deal with the details of this. Excellent, good place to stop. So where are we heading? We're going to play around with these equations. You should learn to play around with them yourself, doodling on the paper. Problems are very easily dealt with. I'll show you how problems get set up. And if you be able to do one, you'll be able to do them all because there's a system. The person who sits down at the table, looks at an equation, says, how can I put words into a problem to deal with that equation? And he does it. Okay, we'll also deal with the specific heats of gases. We'll go from monatomic to diatomic. It's a very simple transition. Diatomic cases, you have extra degrees of freedom. Two others specifically. We'll talk about that the next time. We're still in ideal gases.